Hi everyone. The major goal of chemistry is to make new materials. So these new materials can be for constructions, for clothing, for food, for medicine, or other stuff. Now, when we want to use chemical reactions to make new products, we will encounter these basic questions, which is how much reactants will we need? How much product will we make? Can we make as much product as we thought we could make? All these questions can be answered if we understand something called reaction stoichiometry, a topic we will cover in Chapter 8. The word stoichiometry itself means measurement of proportional quantities, which is what we do when we run a chemical reaction. The best analogy to calculating quantities in chemical reactions is when you use a recipe in cooking. Let me show you what I mean. Let's say you have the following recipe to make a pancake. 1 cup of flour with 2 eggs and half a teaspoon of baking powder gives you 5 pancakes. This is obviously a pretty bare bones recipe, right? It doesn't tell you exactly how to mix these ingredients or how long or at what temperature and so on. But it gives you an abbreviated recipe for making pancakes. But that's exactly what a balanced chemical equation is. So if I write 3H2G plus N2G goes to 2NH3G, it's the same idea. It's an abbreviated recipe for making NH3 gas or ammonia. Now, let's go back to our recipe. What it gives us is a way to relate one ingredient with another, doesn't it? So here is how you can interpret the recipe, assuming all the other ingredients are available. Now, that's a really critical assumption, as you'll see later. So let's say we have 2 eggs. We know it's going to give us 5 pancakes. Again, assuming that all the other ingredients, in this case flour and baking powder, are available. Or we can say that if we have 1 cup of flour, we'll get 5 pancakes as well, assuming there's lots of eggs and lots of baking powder. We can also say that if we have half a teaspoon of baking powder, they'll give us 5 pancakes, assuming there's plenty of eggs and plenty of flour. Now, this is useful because we can now write it as a conversion factor. The conversion factor would look something like this: 2 eggs over 5 pancakes, or we can flip it and say 5 pancakes for every 2 eggs, okay? Now let's see how we can use these conversion factors. Let's say a friend asks you, if I have 8 eggs, how many pancakes can I make? Well, the answer is pretty straightforward, because what you can do is say, take 8 eggs and multiply that by the conversion factor between eggs and pancakes. Now in this case, we want to cancel our eggs, so we would use this form of the conversion factor where the eggs here is on the denominator, so we can cancel that out with this eggs. So 8 times 5 over 2, that gives us 20 pancakes. So that means if I have 8 eggs, I can make 20 pancakes. Now you could have done this in your head also, but it's helpful to write it out in the equation the way we've been doing for dimensional analysis, because that's what you'll do later when we're doing chemical equations. Let me show you one more example of how to apply the idea of that conversion factor to figure out the relationship between the ingredients. So we can look at this questions where it says, if we have 5 cups of flour, how many eggs do we need to complete the recipe? So we start with 5 cups of flour. We'd multiply this with a conversion factor between the eggs and the cups of flour. And based on the recipe that we're given, 1 cup flour is proportional to 2 eggs. So we would put 2 and 1 here. And that would mean that if we cancel out the units for cups of flour, we get 10 eggs are needed for 5 cups of flour. Okay, so how would this work in an actual chemical equation? Well, as I said earlier, the equation is your recipe. The only difference is that in a chemical equation, the relationship between one species with another is in units of moles. This is different compared to the cooking recipe that we just looked at, where the relationship is expressed in various units. Cups versus teaspoons versus number of eggs and so on. In a chemical equation, the relationship between hydrogen and nitrogen here are in moles. So in the equation that we have here, what it means is that if we have 3 moles of hydrogen, it will produce 2 moles of NH3, assuming there's enough nitrogen available. So the way we interpret the equation is the same as our recipe, except that you have to make sure that all the units are in moles. So what we often say is that the equation gives us a mole to mole ratio between the species. That means we can write conversion factors, just like we did in our recipe. We can say 3 moles of H2 over 1 mole of N2, or 3 moles of H2 over 2 moles of NH3, or 2 moles of NH3 over 3 moles of H2. Let me show you an example of how to solve a chemical equation problem using the mole relationship we just talked about. In this case, it says consider a reaction between sodium metal and chlorine gas to make sodium chloride, and we're asked to do a couple of things here, write the balance equation and calculate how many NaCl in terms of moles would you get as a result of a complete reaction with 3.4 moles of Cl2. So the first thing with these type of stoichiometry questions is always to write a balance equation. And so we have sodium metal, which is Na in a solid form, chlorine gas, which is Cl2, and it forms sodium chloride. The other thing we need to do with this is to balance it. So to balance, we would put 2 and 2 here. And after that, we have to calculate the number of moles of NaCl that we would get. And to do that, all we need is to start with the thing that we're given, which is the number of moles of Cl2, and multiply this by a conversion factor for Cl2 at the bottom and NaCl at the top. And the conversion factor comes from the equation itself. So in this case, we have 2 for sodium chloride and 2 for sodium. So we would just put 2 over 2. And so, of course, that means we end up getting 3.4 mole sodium chloride.